fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live.
When NASA confirmed that R2 Swan was speeding on a trajectory toward Mars, it set the scientific world and the public imagination ablaze. Rarely does a single discovery ignite such a fusion of anticipation, speculation, and wonder. Yet this event managed to do so almost instantly. The official announcement itself was succinct, factual, and carefully measured, but what it implied was vast. A celestial traveler, unseen by humanity until recently, had been caught crossing space at a velocity that drew immediate comparison to comets, interstellar objects, and deep space probes. Only this one was hurtling toward the red planet. That knowledge alone was enough to shift the narrative of near-term planetary science and exploration, as suddenly Mars had become a stage for an uninvited but extraordinary arrival. Before we start, smash the like and subscribe buttons for more updates. The designation R2 Swan was not just a name but a key to its discovery. NASA teams had been surveying a swath of sky with updated detection networks, scanning for transient bodies that pass through the solar system. The Swan designation linked it to a particular observatory program, while the R2 identifier marked its classification in sequence. To learn that this body had not simply wandered into the inner solar system, but was in fact heading directly toward Mars, elevated its importance immediately. Unlike the many objects cataloged in near-Earth databases, R2 Swan was now tied to a destination that humanity has long set its sights upon. The trajectory was no longer abstract. It was a precise mathematical certainty that bound this object to Mars's neighborhood, and that fact unlocked a surge of curiosity. As details emerged, what gripped experts was the speed. Reports highlighted that R2 Swan was moving with an unusual velocity, one that suggested either an interstellar origin or a unique gravitational push from interactions elsewhere in the solar system. Objects that race at such speeds carry with them stories written in the language of cosmic mechanics. Scientists immediately began considering whether Swan was a comet-like body rich with ice, dust, and volatile material, or whether it represented a rarer class of rocky traveler with more enigmatic origins. The nature of this body would dictate not only what might happen when it reached Mars's orbit, but also what it could reveal about the pathways objects take across interplanetary space. The prospect of such a fast object intersecting with Mars opened new avenues of thought. For decades, Mars has been both a target and a symbol for exploration. It is the planet where rovers crawl, satellites circle, and human dreams gather in blueprints for crewed missions. To imagine a fast-moving body approaching Mars created a sense of urgency that stretched beyond the labs and into mission control centers. Teams responsible for orbiters like Mars Reconnaissance, Orbiter, and Maven began running simulations, calculating whether R2 Swan's approach might give them observational windows. An object moving at high velocity provides only a fleeting chance to capture data, and planning had to be swift. Unlike the long lead times of scheduled missions, this was a cosmic surprise, demanding rapid mobilization. Part of the fascination lay in the fact that Mars would be the backdrop to this event. Unlike Earth, where atmospheric density often breaks apart incoming bodies before they reach the surface, Mars has a thinner atmosphere. This means an object arriving at the speeds associated with R2 Swan could potentially penetrate deeper before dispersing, or even strike the surface if its path intersected perfectly. Though NASA did not frame the announcement in terms of catastrophe or danger, the physics of such a scenario were hard to ignore. Even without an impact, the approach itself promised fireworks of a kind unseen in human history. A natural high-speed visitor streaking across Martian skies while instruments recorded the show. For planetary scientists, the implications stretched further still. If R2 Swan was interstellar, like the famous objects Oumuamua and 2I/Borisov, then its path through the solar system offered a gift of comparative science. Every interstellar visitor is a sample of conditions outside our solar neighborhood, carrying compositions and histories that formed around other stars. To have one pass close enough to Mars for multiple spacecraft to study was unprecedented. Suddenly, Mars was not just a target in our solar system, but a vantage point for observing something that might never come again. The convergence of these circumstances, the planet with robotic observers and the cosmic traveler, felt almost orchestrated by the universe. On the public side, the announcement carried with it the thrill of space drama. News channels emphasized the speed, calling it a cosmic bullet, while social platforms filled with animations of a glowing streak converging with the red planet. The excitement was not rooted in fear, but in awe. Humanity has always craved stories of visitors from the stars, and here was a real one announced by the premier space agency on Earth. The sense of immediacy, that something extraordinary was happening right now in the vastness beyond, sparked a shared moment of wonder. People could look up at Mars, a reddish dot in the night sky, and imagine R2 Swan racing unseen through the void toward it. Meanwhile, within the scientific community, the announcement spurred debates about what exactly should be prioritized. Some argued that orbiters should redirect attention to capture every possible data point, spectral readings, images, dust analysis, while others cautioned that overcommitting resources could compromise long-term objectives. Yet the consensus leaned towards seizing the chance. Rarely does a natural event align so perfectly with our robotic presence on another planet. The instruments orbiting Mars, designed for atmospheric sampling and geological mapping, suddenly had a chance to record a visitor that carried information from possibly beyond the solar system. It was a scientific opportunity too valuable to let pass. The trajectory itself became a focus of obsessive analysis. Computers modeled its path again and again, refining the precision of its arc as it swept inward. Each recalculation brought clarity, but also new speculation. Would it simply skim past Mars, offering only a visual spectacle? Or would it cut closer, interacting with the thin Martian atmosphere in a way that produced measurable phenomena? Teams considered whether faint tails of ionized gases might trail behind it, if Swan was cometary in nature, and whether those emissions could alter the composition of Mars's sky even for a brief moment. Every scenario added layers to the unfolding drama. Underlying all of this was the awareness that events like R2 Swan remind humanity of its place in a dynamic universe. While we map, chart, and plan, the cosmos continues to send surprises our way. NASA's announcement was a recognition of that truth, a way of saying that despite all of our advances, space retains the ability to surprise and humble us. The fact that this surprise intersected with Mars, a planet we are actively exploring, felt like an alignment of destiny and science. In an era where attention spans are often fleeting, this event managed to root itself firmly in both the public consciousness and the long-term work of planetary exploration. The scale of the object itself remained part of the intrigue. Observations suggested it was not vast, certainly not on the scale of a major asteroid, but size mattered less than speed in this case. An object moving so quickly has immense kinetic energy, and its encounter with Mars, whether near or direct, would be an event of consequence. The very act of measuring its brightness, spectrum, and tail, if any, as it approached, would tell scientists more about its size and composition. To have this kind of data in tandem with its rapid motion provided a chance to expand our catalog of cosmic bodies in ways that static observations from Earth could never fully capture. Another dimension of the excitement was what this meant for the future of planetary defense and interplanetary readiness. While R2 Swan was not considered a threat, its sudden emergence underscored the importance of detection systems that can identify fast-moving objects on potentially collisional paths. The fact that it was heading to Mars rather than Earth did not diminish its significance. Rather, it became a reminder that the solar system is a stage of constant motion, where planets and bodies weave in complex dances that occasionally intersect in dramatic ways. Learning from Swan's approach could help refine models for how we detect, track, and understand similar bodies in the future. The cultural imagination, too, found fertile ground in this moment. Mars has always held a mythic quality, from ancient civilizations who saw it as a god of war to modern storytellers who envision it as humanity's next home. To combine that mythology with a real-time cosmic encounter transformed the narrative again. Mars was no longer just a destination of human ambition, but also a host, a planet about to receive a guest from deep space. The symbolic power of that idea resonated as strongly as the scientific reality, reminding humanity that space exploration is as much about inspiration as it is about data. NASA's announcement also fueled discussions about how humanity engages with cosmic events. In the past, a discovery like Swan might have been confined to academic circles until long after its passing. Today, with near-instant communication, the knowledge was shared globally in real time. That democratization of discovery meant school children, amateur astronomers, scientists, and ordinary dreamers all learned of Swan together, each able to imagine what it might mean. The immediacy created a sense of collective participation, as if the whole world was leaning closer to see what would happen next. The precision of the tracking also became a point of pride. To announce with confidence that a body was heading toward Mars at speed showed just how advanced our observational capabilities had become. It was not guesswork, but carefully validated science, the result of countless hours of monitoring, calibration, and calculation. Behind the headlines lay a quiet triumph of astronomy and engineering, a testament to the networks of telescopes and the expertise of the teams that bring such hidden travelers into view. Even as excitement mounted, the language of the announcement was careful. NASA avoided dramatic framing, instead grounding the event in observation and data. Yet the careful words did little to contain the firestorm of wonder that followed. That balance between scientific caution and public fascination has always defined space exploration. In this case, it heightened the drama, allowing imagination to flourish while scientists prepared for the sober task of measurement and analysis. The knowledge that R2 Swan was fast and heading directly toward Mars was enough to mark the event as singular. Every planetary encounter with an interstellar or high-speed body is unique, but this one coincided with a moment in history where humans had the tools to watch, study, and learn. That convergence was rare and precious, a reminder that space exploration is not only about the missions we launch, but also about being ready when the universe decides to surprise us. For Mars, for science, and for humanity, the announcement was not merely news, but a threshold into discovery, a moment where the known and the unknown brushed against each other in the dark corridors of space. The speed with which R2 Swan was confirmed to be moving was not just a curiosity, but a fundamental driver of new scientific questions. Velocity in space is never an isolated factor. It speaks volumes about an object's origin and the forces that have shaped its journey. The unusually high speed of this body demanded explanations. Some scientists speculated that it may have been dislodged from the outer reaches of the Oort cloud, hurled inward by subtle gravitational nudges over millennia until it gained momentum near one of the giant planets. Others push further, proposing the possibility of an interstellar genesis. In that scenario, R2 Swan would not be a resident of our solar system at all, but a traveler from beyond, carrying within its structure the ancient record of a star system light years away. The prospect of Mars being the stage for such an interstellar visitor made the announcement all the more astonishing. To understand the significance, it helps to recall that interstellar objects observed before have only fleetingly passed through our skies. Oumuamua swept by without warning, and 2I/Borisov offered a cometary glimpse before vanishing into the deep. Both were studied from Earth and through telescopes positioned across our planet. This time, however, the visitor was not passing by Earth, but heading directly toward a planet that already had a fleet of orbiters and rovers at work. That difference changes everything. Instead of relying on distant observatories from one vantage point, humanity suddenly had the means to examine a cosmic wanderer in situ, as though Mars itself were an outpost prepared for such an encounter. The simple coincidence of timing, a body from beyond arriving where humanity has machines waiting, struck many as a gift of cosmic proportion. Attention quickly turned to what instruments could be repurposed to observe Swan. Cameras designed to map the surface of Mars could be redirected skyward. Spectrometers intended to analyze atmospheric gases could be pointed outward to detect emissions from Swan's surface. Even orbiters not designed for such work, like communication relays for rovers, could provide positional confirmation and tracking assistance. The question was not whether to observe, but how to coordinate an interplanetary orchestra of instruments to catch as much data as possible during the fleeting window of Swan's approach. Every moment of that window mattered because at its incredible speed, the object would not linger. The difference between success and failure could come down to hours, even minutes. Beyond the immediate science, there was the sheer spectacle of imagining what might unfold. If Swan had volatile ices within it, as comets do, then heating from the sun as it drew closer to Mars could produce jets and tails. Such activity could fill the Martian sky with streaks of light visible to orbiters circling above, and perhaps even to rovers peering upward from the dusty surface. These rovers, designed to study geology and climate, were not intended as skywatchers, but the chance to have their lenses aimed at Swan added a poetic dimension. Machines built by humans, sitting silently on a planet millions of kilometers away, could end up photographing an alien traveler racing past. That image alone stirred imaginations across the world. As speculation spread, so too did discussions about the potential consequences for Mars itself. While the chance of a direct impact remained slim, even a near pass could have subtle yet fascinating effects. Dust streams released from Swan could brush against the upper layers of Mars's thin atmosphere, producing auroral glows or other luminous displays. The magnetosphere interactions recorded by MAVEN could spike dramatically, offering new insights into how Mars responds to incoming matter from space. And should Swan release substantial material, some of that dust could eventually settle on the surface, mixing with Martian soil and creating a lasting trace of the encounter. Such deposits, if ever sampled in future missions, could provide a direct laboratory of interplanetary or even interstellar matter delivered to Mars. The sheer improbability of it all amplified the significance. Space is vast, and planetary alignments with fast-moving bodies are rare. For Swan to cut across Mars's orbit precisely while humanity has the means to observe is an alignment of circumstance bordering on miraculous. Scientists are careful to avoid framing cosmic events in terms of destiny, yet the sentiment crept in nonetheless. This was not just another object to log and dismiss, it was a narrative moment, a rare page in the history of exploration. It underscored the fact that space is not a static canvas but a living stage of constant, unpredictable movement. Meanwhile, teams on Earth began to refine theoretical models to anticipate Swan's behavior as it neared Mars. Would its high speed mean it remained intact, or would gravitational and thermal stresses cause it to fragment? Fragmentation would present new opportunities, as smaller pieces could interact differently with Mars's atmosphere and surface. A fragmented Swan might deliver multiple observable events rather than one. Each fragment would provide its own trajectory, its own interaction, its own story to tell. That scenario became a focus for mission planners, who began preparing contingency observations for multiple possible outcomes. For Mars exploration programs, Swan's approach was a moment of unity. Different missions, often siloed with specific objectives, suddenly had a common target. Collaboration among teams that typically worked independently became essential. NASA's coordination with international partners like ESA, which also has assets around Mars, grew rapidly. It was no longer just a NASA story, but a global one. Every instrument in orbit or on the surface became part of a larger network, and the object heading toward Mars transformed from a curiosity into a rallying point for planetary science at large. Public enthusiasm mirrored the scientific momentum. Interest in Mars has always been strong, but Swan's arrival injected fresh vitality into public engagement. Artists rendered dramatic illustrations of a luminous streak arcing above Martian canyons, while educators folded Swan into lessons on astronomy and physics. Amateur astronomers organized virtual watch parties, tracking its progress from Earth as data became available. The sense that humanity was collectively watching something grand unfold made the announcement feel like the beginning of a shared adventure. For a public often hungry for wonder, Swan provided it in abundance. As more data came in, estimates of its composition began to circulate. If Swan turned out to be rocky, its survival through space at such speed would tell scientists much about the resilience of small bodies. If it were icy, then its potential for volatile release would raise questions about how far such materials can endure journeys between stars. Either case added to the fascination. For decades, planetary scientists have theorized about the exchange of matter across star systems, suggesting that rocks and ices could carry organic compounds, or even the seeds of life. Swan offered a rare chance to test such ideas in real time. The thought that Mars might soon be dusted by interstellar particles was enough to reignite long-standing debates about panspermia and the interconnectivity of worlds. Another thread of conversation emerged around what Swan's speed revealed about gravitational corridors in the solar system. Every object's path is influenced by the gravitational fields of planets and the sun. High-speed bodies like Swan trace lines that reveal these invisible networks. Studying its trajectory closely could sharpen our understanding of how interstellar travelers navigate the gravitational architecture of the solar system. Such knowledge is not only academic but practical, helping refine models for the paths spacecraft might one day take on interstellar journeys of our own. In this way, Swan was not just a visitor but a teacher, offering lessons that could guide humanity's future across the stars. The timing also intersected with a larger cultural moment. Humanity stands at the edge of a new era of exploration, with multiple missions planned to carry humans to Mars in the coming decades. Swan's approach seemed almost symbolic, as if the universe were sending a herald to the planet we dream of visiting. The event underscored how alive Mars is, not biologically perhaps, but dynamically as part of the great celestial dance. It reminded us that Mars is not a still target waiting for our footsteps, but a world immersed in cosmic motion, intersected by travelers like Swan who add complexity to its story. As anticipation built, the question of observation strategy became urgent. Could Mars's rovers like Perseverance and Curiosity lift their cameras skyward at just the right moment? Could orbiters capture the streak against the backdrop of Mars itself? The technical challenges were immense. Rovers had to balance power, communication, and timing, while orbiters had to adjust instruments not designed for high-speed sky photography. Yet the determination to capture Swan's moment of passage was palpable. Mission planners spoke of the chance as once in a lifetime, worth every effort to adapt hardware to this unexpected visitor. Speculative voices also wondered what Swan might reveal about regions of the galaxy humanity has never touched. If interstellar, its materials could be older than the sun itself, formed in stellar nurseries long vanished. Each molecule within it could be a clue to cosmic epochs beyond human memory. To capture such data was to peer not only into another place, but into another time, a kind of cosmic archaeology delivered to Mars's doorstep. The romance of that idea only added to the excitement as scientists and dreamers alike contemplated the deep-time journey that had brought Swan into our awareness. Every new calculation of Swan's orbit also highlighted the fragility of prediction. Though astronomers had refined its path with great accuracy, the universe is never entirely predictable. Small uncertainties remained, and with them the tantalizing possibility of surprises. Perhaps it would pass closer than expected or display behaviors no one anticipated. The very act of watching, of waiting to see what Swan would do, became part of the allure. The announcement was not an end, but a beginning, a doorway into unfolding mystery. The psychological impact of such events should not be underestimated. Humanity often feels disconnected from the vast universe, locked into routines on a single planet. But announcements like NASA's bring that universe close, reminding us that we are participants in a larger drama. The knowledge that something alien and fast is hurtling toward Mars at this very moment pulls us out of the ordinary and back into awe. It is a reminder that while we may chart our lives with calendars and clocks, the cosmos keeps its own time, and sometimes its rhythms intersect with ours in breathtaking ways. At the same time, Swan's approach raised questions about readiness. Mars is our most explored neighbor. Yet even with all our machines there, we remain limited in what we can do when confronted with an unplanned cosmic event. The scramble to repurpose instruments revealed the flexibility of science, but also its constraints. Future planners began to wonder whether missions should always include contingencies for unexpected phenomena, recognizing that space will continue to throw surprises our way. Swan may well become a case study in the importance of designing with adaptability in mind. The sheer distance involved also framed the challenge. Mars is far, and communication delay means that no real-time commands can be issued to instruments. Every plan had to be pre-programmed, anticipating Swan's passage with exquisite precision. That constraint tested human ingenuity and foresight, demanding that scientists think not in terms of reaction, but in terms of preparation. It was a rehearsal in some ways, for how humanity must operate when venturing deeper into the solar system, where delay and uncertainty will always be greater. As the world digested the news, the beauty of the situation settled in. Mars, a planet already layered with stories of exploration, was about to gain a new chapter. It was not a chapter written by human engineers alone. but by the cosmos itself. A swift, enigmatic traveler was approaching, bringing with it mystery, data, and wonder. The anticipation was not about aftermath or consequence, but about the raw immediacy of encounter. Swan was on its way, and humanity was watching, waiting, and preparing to learn from whatever unfolded. The anticipation surrounding R2 Swan's flight toward Mars did not merely rest on its physical trajectory, but also on the intellectual leap it forced upon those studying it. Rarely does a single event open so many avenues of thought at once, yet Swan's velocity, direction, and timing combined to generate an explosion of inquiry. From the moment NASA's announcement spread, theorists, engineers, astronomers, and philosophers alike found themselves contemplating what this encounter meant, not just for Mars, but for humanity's relationship with the universe itself. One of the most compelling aspects was the chance to study the interaction between a high-speed traveler and the Martian environment in situ. Unlike Earth, with its dense shield of atmosphere, Mars offers only a thin layer of gases. This means Swan's passage through Martian skies, should it graze close enough, might be far less impeded, allowing scientists to directly observe physical processes that are otherwise blurred or hidden on Earth. Hypotheses began to circulate about the potential for shockwaves in the thin Martian air, cascades of ionization that might momentarily alter the planet's sky, or streaks that could be detectable even from Earth-based telescopes. Each possibility provided a natural laboratory for phenomena that cannot be recreated easily elsewhere. In addition, Mars's existing fleet of orbiters and landers provided what amounted to a network of observatories. On Earth, astronomical events are often studied from a handful of points, each separated by thousands of kilometers. Around Mars, however, the orbiters circle at different altitudes, angles, and times of day. Together, they offer a three-dimensional monitoring system capable of capturing Swan's approach from multiple perspectives simultaneously. This accidental constellation of spacecraft could provide stereo imaging of the traveler, three-dimensional mapping of its path, and even real-time tracking of any material it shed into space. The sheer geometry of the observing platforms transformed Mars into something like a cosmic observatory, perfectly positioned to study a passing mystery. Attention also shifted toward the potential for Swan to enrich Mars itself. If it carried volatile compounds or dust, and if any of this material settled onto the Martian surface, then Swan would leave behind not just a fleeting light show, but a tangible deposit. The implications for planetary science were extraordinary. Future sample return missions, already in the planning stages, could stumble upon grains of matter that had originated outside the solar system. Such grains would represent a treasure trove, not only of scientific information, but of philosophical significance. They would be relics of another place, another time, delivered by cosmic chance onto the planet humanity most yearns to explore. This led some thinkers to draw broader connections to astrobiology. If matter travels across star systems, then the seeds of life, complex organic molecules, or even simpler chemical precursors might also be shared between worlds. Swan, in this sense, became a living metaphor for the possibility of panspermia, the theory that life or its ingredients may move through the galaxy on the backs of wandering bodies. Mars, long considered a candidate for ancient or even dormant life, might be receiving a package from the cosmos that aligned with those very ideas. The romance of that possibility could not be overstated, and it gave the announcement a resonance far beyond the confines of planetary science. At the same time, Swan's approach brought to the forefront questions about preparedness and adaptability. Space exploration is typically built on long planning horizons, with missions years in the making and objectives laid out in painstaking detail. Swan was a disruption of that rhythm. It forced scientists to reconfigure priorities overnight, to consider how tools built for one purpose could be repurposed for another. This adaptability, this willingness to pivot when the cosmos presents a new opportunity, may come to define the future of exploration as much as the carefully scripted missions. Swan, in this sense, was not only a scientific object, but also a test of humanity's agility in the face of the unexpected. The approach also underscored how deeply connected observation and imagination are in the practice of science. The bare facts of Swan's existence, its trajectory, its speed, were not in themselves dramatic. What gave them life was the web of possibilities they opened. Each scientist, Each observer layered meaning onto those facts, envisioning outcomes that ranged from luminous skies above Mars to fragments scattered across its deserts. This layering of meaning is what transformed Swan from an entry in a database into a global event. It was not simply that an object was approaching Mars. It was that humanity collectively chose to see in that approach a moment of significance. Equally compelling was the opportunity Swan provided to test and refine models of celestial mechanics. Objects like Swan are not isolated. They are shaped by encounters with planets, stars, and unseen masses. By tracing its trajectory in detail, astronomers could gather new evidence about the gravitational dynamics of the solar system's outskirts and beyond. Swan's high speed implied influences far from the center of the system, perhaps even from interactions with unseen companions like small rogue planets or dense clusters of cometary matter. Each refinement in its trajectory was a clue to the hidden architecture of space, revealing forces at work that might otherwise remain undetected. The announcement also triggered a surge of interest in the engineering side of exploration. Observing Swan demanded more than curiosity. It demanded rapid technical ingenuity. Engineers tasked with reprogramming spacecraft had to find ways to adjust pointing mechanisms, recalibrate sensors, and synchronize operations across vast distances. Each adjustment carried risk, as instruments are delicate and often tuned for narrow purposes. Yet the willingness to stretch these machines to their limits spoke to the spirit of exploration. It was a reminder that space science is as much about human skill as it is about cosmic wonder. Swan was not only an object to observe, but also a challenge to rise to. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on R2 Swan heading fast toward Mars? Exciting or concerning? We want to hear from you. Thank you for watching and see you next time.